for part 1, first I will explain fusion welding. Second, the process of oxyacetylene welding of low carbon steels. Third, oxygen and acetylene equipment. Fourth, safety handling of oxyacetylene equipment and safety procedures. To start off, let's define fusion welding. It's a thermal joining process where we melt the edges of the parent metal to be joined, causing them to fuse together. This can be done with or without the use of a filler material. Now, let's break down some key concepts. First is full fusion. This means that the entire thickness of the material is melted and fused together, ensuring a strong bond. Second is joint configurations. There are two main configurations we encounter. First with filler rod, second is self-supplying. For filler rod, here we use a separate filler rod made of a similar composition to the parent metal being joined. For the self-supplying, in this case, no filler rod is needed. The parent metals fuse together directly. For the welding processes, we commonly use two welding processes. First, gas welding, also known as oxyacetylene welding. Second is metal arc welding, which is electrically powered and often referred to as stick welding. Next, importance of information. It's crucial to provide the welding operative with the necessary information on fabrication assembly drawings. This ensures they can produce the correct type of weld in the correct location. The schematic diagram on this slide shows the comparison of oxyacetylene and metallic arc welding. Now, let's dive into the process of oxyacetylene welding, particularly focusing on low carbon steels. For the process overview, oxyacetylene welding harnesses the power of oxygen and fuel gas combustion to generate the necessary heat for welding. Gas stored in high-pressure cylinders travels through hoses to the handheld oxy-fuel torch. Within the torch, oxygen and acetylene mix in the mixing chamber and exit through the orifice in the tip. This process heats the base metal until it reaches its melting point, facilitating fusion welding. For the welding procedure, when the base metal reaches its melting point, typically around 3200 degrees Celsius, fusion welding occurs. Oxyacetylene welding is particularly suitable for thin metals due to its lower temperatures compared to other welding techniques. Whether to use filler rods depends on the project's requirements. Now, let's move to the essential equipment for oxygen and acetylene welding. First up, we have the oxygen and acetylene cylinders. We can easily differentiate them by their color. Oxygen cylinders are black, while acetylene cylinders are maroon. These cylinders contain the gases under pressure, ready for use. Next, we have the manifold system, which connects multiple cylinders to a single outlet. This setup allows for the simultaneous use of oxygen and acetylene, enhancing efficiency in gas welding operations. Next, pressure regulators. Pressure regulators play a crucial role in controlling the flow of gas from the cylinders to the torch. They ensure that the gases are delivered at the desired pressure levels for optimal welding performance. Then, the welding hose. The welding hose connects the regulators to the welding torch, allowing for the passage of gases. It's a flexible component that enables mobility during welding operations. Next, the welding torch is the handheld device that mixes and directs the flow of oxygen and acetylene to create the flame for welding. It's an essential tool in the welding process, allowing for precision and control. Lastly, the gas economizer is a device that optimizes gas usage, reducing waste and improving efficiency during welding operations. It's a cost-effective solution for maximizing the utility of oxygen and acetylene gases.
Part 2 will be describing types and application of oxyacetylene flames. Part 2 will be describing types and application of oxyacetylene flames. Part 2 will be describing types and application of oxyacetylene flames, the structures of the weld zone, and the various oxyacetylene welding techniques, and explaining the importance of each preparation prior to welding. Oxyacetylene welding uses a control flame produced by burning acetylene gas with pure oxygen. So by adjusting the ratio of these gases, welders can create three main flame types for different effects on the metal being joined. So this is those three flames, which is reducing flame or carburizing flame. The second one is neutral flame, and the third one is oxidizing flame. So this is a diagram that differentiates all those three flames. So the first one is neutral flame. It is the most common and desired flame for welding. It has a balanced ratio of oxygen and acetylene. It does not cause any chemical change in the joint metals. It neither oxidizes nor carburizes the parent and filler metals. It also has two distinct cones. The first one is the light blue inner cone, which is the hottest part, and the second one is darker blue outer cone, as you can see in the image below. So it is ideal for welding most low carbon, stainless steel, steels, cast iron, and also copper. The second flame is oxidizing flame. It is created by introducing more oxygen than acetylene. The extra oxygen helps create thin oxide layer that can protect this base metal in some cases. While generally it is not recommended for most welding, but it can also be beneficial in a specific situation. So it is used for welding some brasses and bronzes or for burning away excess metals during preparation. So it produces shorter, sharper inner cone, and it also produces a roaring sound or noisier sound. As you can see in the image below, it has like a pointed inner cone, and therefore the outer cone it is small and narrow. The last one is carburizing flame, also known as reducing flame. It has an excess of acetylene compared to oxygen. The flame adds carbon to the molten weld pool, which makes it brittle and undesirable in most welds. So it also has a longer inner cone with a feathery shape of acetylene, and it also produces soft hissing sound. And then it has like a blue to envelope the flame. This flame is useful for carburizing or surface hardening ferrous metals and when flame brazing aluminum and its alloy. Next, I'll be talking about the structure of weld zone. So this is the diagram on the right side that you can see of the weld zone. So we have here the penetration bead and the thread thickness and also the reinforcement. So I'll be talking about weld metal zone or fusion zone first. So this is the heart of the weld. During welding, the intense heat melts the base metal edges and any filler material added. This molten metal then cools and solidifies, forming the weld metal zone. So the structure of this zone can vary depending on the welding processes, heat input, and also material properties. So the next one is fusion boundary. So this is the interface between the weld metal zone and the surrounding base metal. So it represents the original age of the molten pool during welding. The fusion boundary can have a distinct line due to the differences in microstructure between the weld metal and the base metal. So the next one is heat affected zone. This zone surrounds the weld metal zone. The base metal here was not melted during welding, but it was exposed to high temperature. This heat affects the microstructure and mechanical properties of the metal, so creating a transition zone between the weld and the unaffected base metal. So the heat affected zone can have subzones with different properties depending on the peak temperature reach. So as you can see on the image on the right side, so we have like the heat affected zone on the different colors of red. So and then the base metal here, and on the center we have like the weld bead, and all the properties of the microstructure is explained on the image. So the next one is base metal. So base metal is the original or unaffected material surrounding the weld zone and the heat affected zone. It retains its original properties. So these four are the structures of the weld zone. So next is oxyacetylene welding techniques. So as you can see on the picture, we have like two welding techniques for specifically for oxyacetylene welding. So on the left side is left word techniques. On the right side is right word technique. So these both techniques are different depending on the material thickness and also welding position. So the first technique is leftward welding. So leftward welding is when the flame is directed away from the finished weld and towards the unwelded part of the joint, which is moving the torch from right to left. So, and also the filler rod, when required, is directed towards the welded part of the joint and angled slightly towards the direction of travel, which is usually 30 or to 45 degrees. And the torch is also held at an angle of 25 to 90 degrees, depending on the material thickness. And this type of technique is ideal for thin sheets, up about 5 millimeters in flat position. It also offers good control and weld penetration for thinner materials. It also used for low carbon steels when making first flange edge weld when the parent metal is less than 1.2 millimeters thick. And basically these welds do not require a filler rod. And the second one is square bar welds on sheet steel with unbeveled edges up to 3.2 millimeters thick. The third one is V-bar welds on steel plate with beveled edges between 3.2 millimeters to 5 millimeters thick. So the leftward methods of welding is considered to be uneconomical when making joints in metal over 5 millimeters thick. So as I've mentioned before, so these are the techniques used in leftward welding, which is flange edge welding, square butt welding, and V-butt welding, as you can see on the picture or the diagram. So on the right side, on the top right side, we have like the flange edge weld. On the bottom right side is a square butt weld, and on the left side, we have the V-butt weld. So you can see all the differences and how the angles of direction. So the second technique is rightward welding technique. So it's basically is when the flame is directed towards the metals being deposited, which is moving the torch from left to right. So it is the opposite of the leftward techniques. And the filler rod angles slightly in the direction of travel. The torch is typically closer to 90 degrees for better heat penetration into the thicker material. It is usually used for thicker plates, which is above 5 millimeters in flat or horizontal vertical position. It also requires more skill and control to maintain the good weld pull. So it is used for steel plates which exceed 8 millimeters thickness. For the first one is square butt welds on unbeveled steel plates between 5 millimeters and 8 millimeters in thickness, which is inclusive. And the second one is V-butt welds on beveled steel plates over 8 millimeters in thickness. So as you can see on the picture, so we have like the thickness of plate, and also it shows how the angle between both plates. Next, I'll be talking about the importance of each preparation prior to welding. So each preparation is only possible for certain weld types, and it is also to achieve full welding penetration and cut the edges of the metals. It is also sometimes called beveling. It is a critical step before any oxyacetylene welding process. So there are a few reasons why it is beneficial. First, it produces stronger and more reliable welds. So you can also gain proper penetration. What I mean by proper penetration is proper edge prep allows for deeper weld penetration, creating a stronger bond between the joint pieces. So without it, the weld might only sit on the surface and create a weak connection and can cause failure on the stress. So the second one is complete fusion between the parent and the joint metal. So the adequate edge prep ensures good melting of the base metal edges and any filler material added. This complete fusion creates a homogeneous weld zone with better strength and fatigue resistance. And the second one is efficiency and safety. So it can also reduce welding time, and with proper edge prep, it reduces the amount of filler metal needed and minimizes the time spent to weld. So this translates to increased efficiency and lower welding costs. So the next one is better control of the weld pool. So a prepared joint allows for better control of the molten weld pool, and this reduces the risk of overheating or burning through the metals or creating excessive spatter, which can be hazardous. So therefore, it can produce high quality results and also minimize the cost.
For part 3, I will be describing the effect of oxide formation and the means of its avoidance, as well as the process of manual metallic arc welding, also known as stick welding. I will also be discussing the types and uses of electrode coatings, as well as the difference between welding with a direct current and welding with an alternating current source. Oxide formation. Oxides form on metallic surfaces when they react with oxygen in the air. This process is sped up in the presence of high heat, a catalyst, or excess oxygen in the atmosphere. The characteristics of oxides are that they have high melting points, low electrical conductivity, are rapidly forming, and are tough to remove, both chemically and mechanically. The effects that oxides have on the welding process is that they hinder the fusion of metals. They might cause inclusions when welding is performed, and due to these flaws and inclusions, the weld might be weaker. The metal while welding might be completely liquid, but then the oxides might remain solid, and this will cause issues in welding. There are many preventative measures for oxidization. The first one is the use of flux. Flux is a material that reacts with any metal oxides or impurities on the welding surface. Flux can be added topically, as in the form of a paste, or it will be in the form of a powder coating on the electrode. The flux forms a hard shell that known as slag that is then easily removed after the welding is done. The second form is to use shielding gas. In MIG welding, for example, an inert gas such as argon is flown over the welding surface, preventing any oxygen from the outside air from reaching the weld. This prevents oxidization. The third type to prevent oxidization from forming whilst welding is to weld in an oxygen-free environment. This is not as common, But if the welding is taking place in an oxygen-free environment, minimal oxidization will occur given that a high oxygen oxyacetylene torch is not used. Manual metallic arc welding. Manual metallic arc welding, also known as stick welding, is a metal fusion process that involves melting an electrode, usually one with a flux coating, to fuse and fill a desired gap in the metal. This takes a process of 5 steps. First of all is choosing the correct type of electrode. Since the electrode is the one that melts and fills in the gap, a correct one according to the material and the flux and the usage needs to be chosen. The second step is striking the electrode against the work surface. This is usually to generate an arc between the workpiece and the electrode. The angle of the electrode needs to be kept in order to get the desired effect from the arc, for example, deeper penetration or faster melt rate. A pattern can be done with the melt rate of the electrode in order to strengthen the welds. The arc length of the weld also matters, as then too long of an arc length might cause a splattering and overheating. Electrode classification. Electrode types can be separated by type according to the British Standard of Electrode Identification. Each electrode is given a number which is printed on the packaging and each individual electrode. The diagram below shows how and what each letter in the classification code means and what it stands for. These are the different types and uses of electrode coatings. First is the rutile coating. Rutile is a stable form of titanium oxide that is found in nature. It is used on electrodes as a form of flux to allow it for general use welds and easy slag cleanup. It is generally used in welding root passes, surface level welding, general purpose welds, and fillet welds and final passes. Second is cellulosic coating. This is a coating made of a compound containing cellulose. It is used in welds involving deep penetration. The uses of this electrode are in welds involving pipelines, vertically down welding, as in a very high angle of weld, minimal slag production in applications where not much slag is required, and welding steel of large thickness due to its deep penetration. The last two types of coatings are low hydrogen coatings and iron oxide coatings. Low hydrogen coatings, also known as basic coatings, are used in high strength welds and in crack sensitive applications. This type of coating results in a low hydrogen environment being generated around the weld and greatly reducing the chances of cracking, hence the name low hydrogen coating. Iron oxide coatings, also unique by its color, is a coating that contains iron oxide in it, allowing it for higher deposits of iron per electrode, as well as faster welds and greater weld effectiveness. I will now be discussing different types of welds with different types of currents. First, with direct current welds. Welding machines that utilize direct current do so by rectifying an AC supply or alternative current supply into a direct current one. The electrode that is used to be melted is the positive electrode, as it generates a majority of the heat. Approximately 2/3 of the generated heat is in the positive side of the electrode. This method is also commonly used in MIG welding. The features of this type of welding is that it creates a stable arc as there is no fluctuation, and this causes smoother welds. There is also a low splatter rate and it is easier to strike compared to AC welding. It can be used with most electrodes, as in different types of electrodes with different coatings, but it has a limited usage with different metals, as it is not suited for the versatility of, for example, different types of aluminium. with alternating current welds. An alternating current is used in welding by changing the polarity of the electrodes constantly. This is done in the frequency of 120 Hz, which basically means it is done 120 times per second. This can make the arc very unstable and not as smooth as DC current welding. The features of this type of welding is that it can weld most metals consistently due to the AC welding process removing any oxide layer. It is also generally cheap to buy and operate due to AC current being more available than DC without the need to rectify. There's also no voltage drops even when using long leads, as well as fasting weld rates than DC current. It is mostly used for welding aluminium and magnesium alloys.
So, I will present you for the last part of this chapter, which will describe on the manual metallic arc welding techniques and technique uses in welding that is striking the arc at the angle of the electrode. Next, I will discussing the cause and effects of weld defect and the workshop testing used for weld joint. And lastly, I will explain the principle of resistant welding that consists of spot welding and seam welding. Manual metallic arc welding is a process where the arc is trapped between an electrode flux-coated metal rod and the workpiece, which both the rod and the surface of workpiece melt to create a weld. This benefit of this process is much cheaper than oxy-acetylene welding, as it produces higher temperature and greater amounts of heat energy to welded successfully with thicker sections. Next, arc is produced by low voltage, high amperage current jumping the air gap between the electrode and the joint to be welded. Last, mostly used coated electrodes consist of a flux which will melt uniformly along with the core wire to form a partly vaporized and partly molten shield around the arc stream. Next, the welding techniques number 1 is striking the arc, which the electrode must first touch the work briefly and then withdrawn to the correct arc distance. It has two methods to be used for this technique. First one is scratching motion, which is easier for beginners and when using an NC machine. The electrode is moved across the plate inclined at an angle as you would strike a match. Second one is up and down motion. It requires us to tap the electrode where the work is to begin and then add a slight lift and scratch motion to establish proper outline and prevent the electrode from sticking. Last technique is electrode angle, because when the electrode is inclined at the correct angle, the direction and force of the arc stream causes the slide to form away from the mold well put and ahead of the arc, thus eliminating the problem of slide entrapment. The two methods that can be used in this process are tilt angle, which the angle between the electrode and the work in a plane perpendicular to the direction of electrode travel along the joint. Second one is slope angle, that is the angle between the electrode and the work in a plane parallel to the joint. Weld defect means when the weld matter and parameter affected by the welding process may be divided into three distinct zones, which can be shown in the diagram provided. Weld defect means when the weld matter and parameter affected by the welding process may be divided into three distinct zones, which can be shown in the diagram provided here. First, the actual weld matter zone. Second, the weld penetration zone, that consists of parameter that has been fused during the welding process. And the third one is the heat affected zone, where the parameter not fused has been affected by the heat generated by the welding process. One of the causes of weld defect is lack of penetration. It occurs when the root of the weld base does not reach the root of the joint to weld the opposite surface in the pipe. To correct this discontinuity, you can increase the current and decrease the welding speed or change the joint geometry. The causes of lack of penetration are to low a welding current for the size of electrode, incorrect polarity if allowing direct current welding, the gap between the parameter is too small, incorrect edge preparation, and too large of a root face. Next one is lack of fusion. It occurs when the weld metal fails to fuse with the side wall or joint, or when two weld bits fail to completely join together. At its worst, it can produce serious crack-like defect which reduce the load carrying capacity of the joint. To fix it, we need to clean the weld surface using the correct welding electrode and preheating the metal before welding, and give proper gas flow rate setting to achieve the right amount of shielding, and regularly checking for moisture contamination in the shielding gas cylinder, and lastly is adjustment of welding current and travel speed setting. The causes of lack of fusion is too low of welding current, incorrect polarity if employing direct current, too fast a welding speed, and faulty manipulation of the electrode, and failure to clean the perimeter joint edge of a side, dirt, grease, and other foreign matter. One of the tasks for the workshop testing is macro examination, which an examination of section through a weld with the naked eye or with a magnifying glass. It used to check incorrect profile, undercutting, slight inclusion, porosity and cracks, poor root penetration, and lack of fusion. Next workshop testing is bend test, which a procedure to determine the relative ductility of metal that is to be formed, usually sheet, strip, plate or wire, or to determine soundness and toughness of metal after welding. The specimen is usually bent over a mandrel or specified diameter. Types of bend test for material has two types. First one is thin material, which suitable for specimen cut from sheet metal up to 1.6 mm thickness. The second one is thick material, which suitable for specimen cut from sheet metal more than 1.6 mm thickness. The working principles for resistant welding is the generation of heat because of electric resistance. This generated heat will depend on material resistance, applied current, condition of surface, and applied current time period. The formula shown in this slide is used to calculate the resistant welding, which H is the generated heat and the unit is joule, I is electric current and the unit is ampere, R is electric resistance and the unit is ohm, T is the time current flow and the unit is second. There are so many types of resistant welding, and I will explain two of it, which is spot welding and seam welding, in the next slide. Spot welding is a resistant welding process. This welding process is used primarily for welding two or more metal sheets together by applying pressure and heat from an electric current to the weld area. It works by contacting copper alloy electrode to sheet surface, whereby pressure and electric current are applied and heat is generated by the passage of current through resistive material such as low carbon steels. Next is seam welding. Seam welding is the joint of workpiece made of similar or dissimilar material along a continuous seam. The seam welding can be broken down into two main techniques, resistance seam welding and friction seam welding. This welding method passes an electric current through the sheet of metal to be joined while they are held together by a mechanical force in a like configuration between shaped copper electrodes. So that's all from our group to present Chapter 11 of Welding subject. Bye, thank you.